Pennsylvania, 1882. In a steep, wind-troubled valley cut by Kinzua Creek, a railroad company set out to do something that sounded less like construction than a dare: raise a wrought-iron bridge more than 300 feet above the ground, stretch it for nearly half a mile from rim to rim, and do it with a workforce so small it could scarcely fill a modern office floor. 40 men is the number most often remembered. Fewer than 100 were involved at any one time by other accounts. What matters is the scale of the imbalance. Against them stood a gulf: weather, weight, distance, gravity, and the clock. In just 94 working days, before the age of modern heavy lifting machinery, they would assemble what became the tallest railroad viaduct on Earth. This was not a monument in search of admiration. It was a problem. The railroad needed to get across the Kinzua Valley without dropping into it and clawing back out, along miles of extra line through rough country. Northwestern Pennsylvania, in the late 19th century, was a place of timber, coal, oil, bark, mills, sidings, and speculative ambition. Every unnecessary mile of track meant more grading, more curves, more fuel, more time, more cost. A valley was not scenery to the railroad. It was resistance. It was made geologically. So the real question was never simply how to build a very tall bridge. It was how to defeat a landscape quickly enough, cheaply enough, and lightly enough that the bridge solved the problem instead of becoming a larger one. How do you carry more than 3 million pounds of iron into a remote valley, stand it on masonry piers, lift it skyward piece by piece, and do it without the forest of scaffolding that such a height would seem to demand? How do you make a structure tall enough to sway in the wind, narrow enough for a rail line, broad enough at the base not to fold under its own burden, and simple enough that men with ropes, hoists, gin poles, derricks, and nerves can actually put it together? That is why the Kinzua Viaduct mattered. Not because it was picturesque, and not only because it was briefly the tallest of its kind, but because it belonged to the violent growth of an industrial society forcing itself through mountains, timber stands, and mineral ground. Railroads in this period were not merely transportation systems, they were extraction machines. They pulled forests toward sawmills, coal toward furnaces and lake ports, and profit toward distant offices. In McKean County and the surrounding region, the stakes were economic before they were poetic. A viaduct over Kinzua Creek helped open a faster route toward the markets of Buffalo and the Great Lakes. It promised to compress distance. It promised to turn topography into timetables. If you value this kind of history measured not only in dates and names but in weight, weather, and the labor of hands, consider subscribing. Projects like this can only be understood when we slow down enough to see what people actually had to do. The plan that emerged was daring in its logic. Instead of a massive masonry arch or a heavy cast-iron structure, the designers chose a wrought-iron tower trestle, 20 slender towers carrying the line across the valley, each tower rising from stone piers quarried locally, each section fabricated in advance and sent to the site for assembly. Octave Chanute, the railroad's chief engineer, selected the proposal from Clark, Reeves and Company of Phoenixville, whose work drew on the famous Phoenix column, a patented wrought-iron form that combined comparative lightness with strength. The structure they devised was not thick, not monumental in the ancient sense, not a wall or a dam or a fortress. It was a lattice of force, a bridge that looked, even in photographs, almost too delicate to be real. Yet delicacy was part of the method. Heavy things are difficult to lift. Lighter things can be built faster. The towers were prefabricated in sections at the plant, so crews on site would not need to forge or fabricate iron in the valley itself. The stone for the piers came from nearby hills. The iron came by rail. A temporary track was laid into the valley to help distribute material where it was needed. Long before the first iron section rose against the sky, men had already cut stone, set piers, hauled components, measured alignments, and transformed the ravine into a work site. That stonework mattered. The drama of Kinzua lives in the height of its iron, but the bridge began below eye level, in foundations. More than 100 masonry piers were required. Each leg of each tower would stand on stone and be bolted down. The valley floor and slopes had to be surveyed, marked, excavated, and stabilized. Sandstone and limestone from the local ground were quarried and shaped. Men swung hammers and handled drills, shoved blocks into place, and raised a platform for the structure before the structure existed. The future record-breaking viaduct depended on this slower, less glamorous labor, the setting of stone into earth, accurate enough that iron assembled months later would find its bearings. Then came the ironwork. Here the feat becomes easier to praise and harder to imagine. No modern crawler crane rolled into the valley, no telescoping boom strode from pier to pier. There was no cheap margin for overbuilding temporary support. Contemporary accounts describe a process that eliminated full scaffolding. The first tower was raised with a gin pole. After that, crews used a wooden traveling crane or derrick on the advancing roadway to erect the next tower, and the next, and the next. Iron rods helped support the spans as workers moved across them. Steam hoists and block and tackle systems multiplied the strength of men whose own bodies remained the prime movers on the site. Rope, timber, pulleys, bolts, pins, bars, plates, and patience. That was the machine. Think about the sequence. To build the next section, you first need a place to stand. To get a place to stand, you must trust the section already erected. The bridge became its own tool of construction. One finished tower made the next possible. One completed length of roadway allowed the derrick to advance. The men moved outward above open air, using the work already done as the platform for the work not yet done. It is one thing to read that a bridge was assembled in segments. It is another to understand that every day's progress was a fresh negotiation with exposure. Behind every neat engineering drawing lay a crew stepping farther from solid ground. At its summit, the viaduct stood about 301 feet above the valley floor, as high as a 30-story building. It reached roughly 2,053 feet in length. The tallest tower spread to more than 100 feet at its base, while the trackway above remained only about 10 to 11 feet wide. From afar, the proportions were elegant. Up close, they would have been unnerving. The whole structure was a lesson in how little material can do when arranged precisely enough. But precision is easy to admire after the fact. During erection, precision meant that a misplaced member, a fouled rope, a misjudged lift, or a sudden gust did not merely slow the work. It threatened to throw iron, timber, and men into the valley. The labor itself disappears too easily inside the phrase, built in 94 working days. 94 days sounds like speed. It was speed. But speed is made of bodies. It meant 10-hour days. It meant climbing. It meant hauling. It meant men balancing on narrow members high over the creek, feeling iron heat under summer sun and iron chill in the morning, gripping rope that could stiffen with damp or burn the palm under strain. It meant lifting pieces that were designed for economy but still weighed far beyond anything a person could master alone. It meant reading the movement of a suspended load by eye and feeling when to heave, when to steady, when to hold. One can picture them without pretending to know their names. A foreman on the advancing work, coat darkened at the spine, two men at a tackle line, leaning back in unison, heels skidding in dust and cinders. Another kneeling on a beam, driving a pin home while the piece still trembles from the lift. A rigger, looking down once and then refusing to look again. Men on the ground shouting up through distance that distorts every word. The creak of timber derricks, the rattle of chains, the brief metallic strike that tells the crew a member has found its seat. Around them the valley opens, green and indifferent. Beneath them the creek continues on, as if no argument with gravity were taking place above it at all. This is the part of the story that matters most. Not only that the bridge was tall, but that its height had to be inhabited before it was finished. Someone had to go first. Someone had to climb the incomplete tower. Someone had to trust a temporary support long enough to create a permanent one. When later generations called Kinzua the eighth wonder of the world, the phrase celebrated the object. It did not adequately describe the labor of becoming, and the labor unfolded inside a broader industrial landscape that was itself raw, extractive, and unstable. The region's forests were falling under saws and axes. Hemlock bark fed tanneries. Coal and oil drew capital and speculation. Railroads did not arrive as neutral lines on a map. They reorganized the land around speed and shipment. Valleys became obstacles to be crossed. Hills became cuts to be opened. Streams became alignments to be spanned. The Kinzua Viaduct was a local structure in one sense and an imperial one in another. Local in stone, timber, weather, and workforce. Imperial in the way it bent local geography to the timetable of distant markets. That larger scale can be measured in logistics. More than 3 million pounds of wrought iron had to be fabricated, shipped, distributed, sorted, and lifted. Stone had to be quarried close by and placed accurately enough to receive the iron legs above. A temporary rail line assisted with handling material in the valley. The components arrived not as one sublime object but as innumerable parts. Every one of them had to reach the right pier at the right time. Bridge building at this scale is often described through genius, but logistics is its truer language. The miracle is not that iron exists. The miracle is that iron arrives when needed, in order, with enough coherence that dozens of men can transform freight into structure. And there were other forces pressing on the schedule. Weather, wind most of all. Kinzua was a place where air moved hard through the valley. Later generations would know the bridge as a structure vulnerable to wind, and finally to the tornado that tore much of it down in 2003. But even in the 19th century, the builders understood that height meant exposure. A load swinging at ground level is troublesome. A load swinging hundreds of feet up is a hazard with ideas of its own. The bridge had to be light enough to build, strong enough to carry trains, and stable enough to survive the valley's crosscurrents. That balancing act, between economy and stiffness, between speed and security, is what gives the viaduct its severe beauty. By late August of 1882, the work was done. The wrought-iron viaduct stood completely across the valley, the rails high above the creek, the line continuous, where the landscape had once insisted on interruption. In practical terms, the bridge shortened the route and strengthened the railroad's reach into a resource frontier. In symbolic terms, it announced a new confidence in American engineering, not merely that men could build large things, but that they could build light, high, prefabricated things quickly, with a sophistication of planning equal to their boldness of execution. 6 of its towers stood higher than those of the Brooklyn Bridge. Visitors came to see it. Newspapers and promoters turned it into a spectacle, but trains were the true applause. Every locomotive that crossed was proof that the impossible-looking thing was not ornamental. It worked, and yet the triumph carried its own expiration inside it. Industrial systems do not stand still. Loads grow, engines get heavier. What is adequate for one decade becomes fragile in the next. By 1900, locomotives and rolling stock had outgrown the original wrought-iron structure. The bridge that had solved one generation's problem became in less than 20 years too slight for another generation's appetite. So the viaduct was rebuilt in steel on the original foundations, larger in mass, more rigid, better suited to a railroad world that had already accelerated beyond the conditions of its making. Even this tells us something important about the first bridge. It was not a timeless object. It was a working answer to a moving industrial question. Rail traffic continued for decades. Excursions later turned the crossing into memory, while it was still physically present. By the early 1960s, regular freight service had ended, and the viaduct began its long afterlife as a relic, attraction, and argument about preservation. Then came the tornado in July 2003. 11 towers were ripped from their bases and thrown into the valley, a catastrophe made worse by the condition of rusted anchor points. It was a violent reminder that engineering triumph is never final. Iron becomes steel, steel becomes rust. Foundations outlast superstructures. Weather keeps score over the long term. What remains now is partial, and because it is partial, it may say more than the intact bridge once did. At Kinzua Bridge State Park, a portion of the structure survives as a skywalk. Some of the fallen towers still lie in the valley below, twisted where the storm left them. The site no longer carries coal, it carries memory. Visitors walk out over the void and look not only at what was preserved, but at what failed, what collapsed, what had to be reinterpreted so that ruin itself could become testimony. That testimony should not belong only to engineers, though engineers earned it. It should also belong to the workers whose names were seldom carried forward with the same care as the dimensions of the bridge. The record preserves the chief engineer, the companies, the design patents, the milestones. It is less generous to the men who climbed the members, steadied the lifts, set the bolts, and taught their bodies to live temporarily in a place no human body was meant to remain. They were not incidental to the feat, they were the feat. The bridge was only the shape their labor took after it cooled. So when we look at Kinzua now, at the surviving span, at the empty air where most of the crossing once ran, at the wrecked towers below, at the photographs of that improbably thin line across the Pennsylvania sky, we are looking at more than a lost wonder of railroad construction. We are looking at a society teaching itself how to turn remote ground into infrastructure, and doing it at a terrible intimacy with material reality. The stone had to be cut, iron had to be lifted, rope had to hold, men had to trust what they had just built with their own hands. If you have ever visited the site, or if another forgotten structure has stayed with you, I would be glad to hear which one and why. Places like this rarely survive in memory by accident. In the end, the Kinzua Viaduct endures not because it stood forever, but because it reveals what progress usually hides. The modern world likes its infrastructure finished, silent, and anonymous. It prefers not to remember the temporary tracks laid just to deliver materials, the local stone hauled from nearby hills, the 10-hour days, the wind on open iron, the men inching outward above a valley so commerce could move a little faster. But that is what the bridge was made of, not only wrought iron and masonry, but coordination, risk, exhaustion, judgment, and the willingness of ordinary workers to climb into empty space and build a road there. Even now, with half the structure gone and the rest preserved as memory, Kinzua still says what so much of modern life tries to forget, that the world we inherited was not summoned into being by progress alone, but by human beings whose labor was immense, skilled, and too often left unnamed.